Hey everyone, welcome to a new video. This time we're diving into another paper, Inverse Reinforcement Learning with Natural Language Goals from Amazon. So this is, I think, my favorite paper so far, and that's because the whole concept and what they do is really neat. The whole idea, right, is that we want to learn based off some natural language goal how to either play a game or accomplish some task in an environment through reinforcement learning, or specifically inverse reinforcement learning. So if you don't know what that is, let me give you a quick example and then I'll sort of break it down as we go. So let's start with, I guess, an example really probably everyone knows, Minecraft, right? In Minecraft, there usually isn't one specific goal that, there's I guess there is the end goal of like killing the Ender Dragon, right? But there's lots of other goals you can do, right? You could build a house or kill some zombies or make some armor. There's all these sorts of things you can do. And in reinforcement learning, we essentially want to, or it would be nice, right, if we could specify what we want to do, which of those tasks we want to accomplish with just a natural language goal alone, right? So I could say something like, build a house. Oh, that's not an H, house. And then I would have my little guy, oh gosh, don't mock me for this. But you have your little guy and he builds you your little house. Now, in reinforcement learning, normally what you would have to do is you'd have to specify a reward function and code it, and it gets a little complicated. So that's sort of what we're trying to do here. Now, that's not even the best part of this paper, though, at least in my opinion. The best part is the latter half of it, where it talks about how we can do this with self-supervised learning. And what that means is that we essentially won't have to feed, after a certain point, any data into this program that we'll be writing, or at least looking into. We won't have to feed any more data into it to learn how to do these things. And that's really great when it comes to things like scaling these AI systems, because you can't always be running around, either grabbing examples or data. So the more this can sort of supervise itself and learn to generalize itself, the better the system is. And that's why I'm so excited about this opportunity, or this paper, specifically. Now, just a quick little thing I want to mention on the side. This is part of my Zero to Paper series. That's where I'm starting from essentially nothing, doing this sort of, or looking into this sort of research, and then doing research for myself with the end goal of publishing a paper at a conference. Now, you don't need to check out that series, but the last video specifically has a lot of interesting, or at least relevant, background information, and it's an interesting series altogether. So if you do want to watch it, I'll leave something in the description for you. But also you can keep up with this sort of thing by subscribing, and it really helps out the channel, so do consider. With that out of the way, let's now dive into the paper. I've scrolled down a bit here so that we have some room to work with. The first thing I want to go over that this paper talks about is AIRL. This stands for Adversarial Inverse Reinforcement Learning. Now, I have talked about this in some of my videos before. I'll do a quick recap, though, in case you haven't seen those. Inverse reinforcement learning, so without the A, just IRL, is essentially a type of learning where we're trying to learn a goal or a reward function. So I think the easiest example of this is, or one easy example is chess, right? In chess, you have your little board, blah, blah, blah. And in chess, you have a very specific goal. The goal is always to checkmate the opponent's king, right? That's what you're trying to do. So if you have the king here, and then you have like, what's it called, a rook? Well, you can't have 3 rooks, but you get the point, right? This would be a checkmate. So that's because the rook is surrounding the king. And the idea of inverse reinforcement learning is that given a bunch of examples of games of chess, we would essentially want to try and find or figure out that the goal of the person playing was to checkmate the king. And then once we learn that, we can use other methods, specifically normal reinforcement learning or forward reinforcement learning, to create an agent or some robot that can play chess like this. So the whole goal of IRL is to learn a goal, because from there, or once we know the goal, then we can learn how to achieve it. So adversarial, the A in adversarial inverse reinforcement learning, that is a specific type of inverse reinforcement learning. I won't go into the details of that because, again, I've gone over it before, and really you could supplement this, or not supplement, you could replace this with anything else, and you'd essentially get this similar results. This paper just uses this because this is one of the state-of-art methods of doing this. So this paper also does 2 other things I want to mention right off the bat, which is it's a natural language conditioned reward function, and also a natural language conditioned policy function. policy function. Now, essentially all this means is that our reward function, right? So this goal we're learning, when we're trying to learn what we're trying to do, that's conditioned on natural language. So like a goal, as I said earlier, for the example of, what was it? Minecraft, right? Our reward that we're trying to learn, our reward function, when we're trying to learn that function, that would be conditioned on the goal of kill 10 zombies or make armor. And our policy is the exact same. So when we're trying to learn these two functions, essentially what the reward is and how we achieve our reward, the two models that tell us how to do that, those both receive these natural language inputs. Now, that's sort of the background information here. And the reason it's background information is because this is actually nothing new, and you'll have seen this before if you've seen one of my previous papers. So what you might ask, right, is, well, what has this paper done that is new? Now, what it has done that is new is two things. So let's go over the first thing. The first thing is that it's implemented and made very good use of a variational goal encoder. Sorry, not encoder, generator. A generator. So this is actually a very cool idea that they use here, in VGG for sure. That's just what I'll call it. So the idea in theory, if you know of a variational autoencoder, is actually very similar. Now, if you don't know that, don't worry. I'm going to go over what that is. So let's scroll down a little bit more. And here's the example I want to go over. I'm going to write out a math equation, right? So let's say, and stick with me here. This has a meaning. So 2 plus x equals, let's see, x over 5, something like that, right? Now let's go ahead and solve this. The first thing we're going to want to do, multiply over the 5, is 2x equals x. Then we say 10, or I'm crazy, that should be a 5. And then we say 10 equals, what is this, negative 4x. And then we get x equals, is that 5 over 2, negative 5 halves? I hope I didn't just mess something up. But anyway, we just solved a math equation. Now, there is a reason I'm doing this. And that is, let's say we take this example of me doing math, right? So like a video of it, right? Or a trajectory of it specifically. And we feed that into our, or I'll draw it again down here, our VGG, so our goal generator. Well, what this goal generator will do, we train it to essentially spit out several different things. So, and these are going to be natural language goal instructions. So it could spit out solve for X, or it might spit out solve the equation. So essentially what it's doing, right, is it's looking at what I did, and then it's printing out or outputting, right, some goal that it thinks I might have been trying to achieve. Or sorry, not even a goal it thinks I might have been trying to achieve, just something that describes what I was doing. So solve for X, I was solving for X, and I was also solving the equation here. They're just two different ways of saying what I was doing, right? And you can imagine in more complex tasks, you might actually be able to generate a lot of different things here, because sometimes you're doing multiple things and there's multiple ways or lots of ways to describe what you're doing. So this is the basis or the backbone for pretty much everything they do here, and I will admit it's very clever. So there's 3 specific ways they use this initially to do essentially data augmentation. So those 3 ways, and you'll see them down here in the paper on the left, so I'll point them out if you want to read this. There's expert goal labeling right here. Oh, not crossing it out, just meant to underline it. Then there's hindsight goal relabeling. And there is hindsight goal sampling. So they also do have a 4th. We're not going to talk about it because it doesn't work very well, as they point out in the paper. So let's talk about these 3. First, expert goal relabeling, or EGR for short. So what EGR does is it happens before training. And we essentially go through all the expert examples, because remember, this is inverse reinforcement learning, so we're trying to learn a goal from examples we've been given. And these are examples of someone doing the task we want to achieve, like checkmating a king. So for each of these examples, we're going to go through and essentially pass them in to our VGG. So pass examples into VGG. And what this does is it outputs a bunch of natural language goals. And after we get those natural language goals, we're going to put back, and I'm just going to call these expert examples. And what this essentially does, or what the effect that it has, is that we had all these examples before we started, right? So maybe we had like each one of these dots is an example. And the more examples we have, the easier it is to learn, right? The more data, the better, essentially. That shouldn't really be any surprise. But we have a sort of we have just this many points of data. What we're essentially saying is that let's just add, how can we add more points of data? Well, what if we take each of these points and we have the same data there, the same trajectory, the same video, so to say, of what's happening, but we label it with a different goal. So we say, in the case of the math example, right, instead of solving for x, it might be solving a math equation. That would be another point here. And we're essentially using this able to fill up a whole lot more examples here. So the more examples we have to work with, the better. So that's essentially what we're doing here. Now, there's two more ways we do this, or augment our data, and they're very similar to this, so they shouldn't take too long. The first one is Hindsight Goal Relabeling, HGR for short, and it's the same as EGR, right? The one we just talked about. However, we do it during training. So I should say but. So it's the same as EGR, what we talked about before, except for we do it during training on trajectories from learned policy. So what does this mean? Well, essentially what this means is when we are training this adversarial inverse reinforcement learning, one of the steps that it requires in its training algorithm is to generate, we're essentially training a policy, right? Training a policy while we're learning the reward. And it requires us to generate new trajectories. So what we're doing is we're taking those trajectories and we are relabeling. Or I guess I should say not relabeling, but we can say generating labels. So a really good example of this, and this seems a little bit weird at first, but is the example, I think, of doing like a backflip into a swimming pool, or like a flip into a swimming pool. Now, you can imagine if that's what we're trying to do in our expert pool, we will probably have an example of that, right? We'll have an example of someone doing a backflip into a swimming pool, and it says, man does a backflip into a swimming pool. Now, when we try to replicate that with our agent, let's say we mess it up and we do, instead of a backflip, we do a backflop, and it is very painful. Well, we can't label, we don't want to like put that normally in our examples we're learning from, right? We don't want to learn how to do this the wrong way. But the key here is that we're not labeling this backflop, this mistake, as a backflip. We're labeling it as a backflop. So we're expanding the horizons of what we can learn. And by doing that, we are hoping essentially that our agent will be able to generalize better to a whole lot of different things. That's the idea behind this. So we generate labels and add to expert examples. So even though our policy might not be very good that we're currently learning, it is probably an expert in doing certain things, even if those certain things are failing, or maybe getting part of the way there. So this is also sort of, it's very similar to curriculum learning, I think, except for a little bit more generalized. Kind of interesting how you do this. Now there is one more thing, and that is HGS, which was that Hindsight Goal Sample? No, Hindsight Experience. No. It's up here somewhere. Hindsight Goal Sampling. Yeah, okay. I think I got that the first time. Hindsight Goal Sampling. And this is literally the same thing as HGR, the one we just talked about. It's the only difference here is except, and I'm sorry for my handwriting, by the way, except use goals from HGR. All I'm saying here is that we're doing the exact same thing, except for the goals. So when we're generating these trajectories, at first they only come from the original expert examples, those goals that we started with. Now, as we go on in the training process, because we're adding to the expert examples in this step right here, well, we're going to end up with new goals, right? HGS is the same thing that I just told you about, except for we're using these new goals, right? We're using these new goals right here. And I don't know, honestly, why they call these two different things. It's essentially the same thing. But anyway, those are the 3 different ways that they do data augmentation in this paper. Now we can look down here on the left and you'll see the final algorithm laid out in whole here. This is a lot. That being said, you don't read through the whole thing, honestly. All you have to know is it's essentially what I just told you. This is the the adversarial inverse reinforcement learning training loop with 3 things added: EGR, HGS, and HDR. So with the exception of those 3 things, it's just normal inverse reinforcement learning. They are just very, very meticulous in writing out this algorithm, honestly. So that's pretty cool. This is a very interesting way to do this, but the paper does even go beyond this, and I think this is actually the most exciting part, because what it does is, if you look again down the bottom left here, we have self-supervised learning in new environments. Now this is kind of crazy. What this is essentially saying is, well, we learned all this stuff in one environment. How do we leverage what we've learned and now apply this to another environment, even if we don't have data for that environment, which is really important, right? And the reason it's so important is because, you know, if you're trying to make a general agent that can do all sorts of things, maybe it can play chess, it can play Go, it can do backflips, it can search the web, I don't know. But you can't spend time making examples for all of these things, right? That's just too much. So what you have to do is that's the whole point of a general agent, right? It should generalize to new environments without you having to spoon feed it like all this new data. So the way they do this is through a 4-step process. So I'll write that out here. So self-supervised steps. Now, step number 1 is to train a goal, I think as they call it, goal agnostic policy. Now, they do this by essentially doing behavior cloning on the old environment. So I should tell you the environment they use in this actual paper is a 3D navigation data set. So if we scroll down here, we should be able to see here. So they have essentially these pictures of a room and they can navigate sort of around them. And essentially all the goals are like, you know, take a left at the next door and then walk down the stairs until you're in front of a brown chair or something like that. So that's all they're trying to do here. And for them, these different environments are like different houses and such. So if we scroll back up here, when I say train a goal agnostic policy, it means that regardless of what the goal is, whether you want me to go down the stairs or open a door or whatever, we're just going to train a policy. And this is after we've done everything I talked about before, right? Once we've learned a policy that can already execute these goals in one environment, well, then we retrain a new network on essentially using behavior cloning. And I'm sorry, I don't think I have time to go into behavior cloning in this video, but there's plenty of resources online about it. But we're essentially roughly copying the policy if we take out the goals, right? So without the goals, it's copying the policy. It's like the priors of what we would do, right? So if we don't have any goal, what's most likely to accomplish what we were trying to do, even though we don't, it's hard to explain, but that's essentially what we do. So we end up with a new goal agnostic policy that just essentially, it's not random actions, it's just taking the priors. So once we have that policy, sorry if that was a bad explanation, but once we have it, what we do is we sample trajectories. So what this means is we just go through and we do a bunch of simulations and see how they play out. Maybe we'll fall down the stairs a few times. Maybe we'll open some doors, go into some random places. I don't know exactly what's going to happen, but we sample a few trajectories. And then we use, step 3 is we use the VGG, the goal generator, the variational goal generator, to essentially create, so we take each of these trajectories and we run them through the VGG. And then we get out, what do we get out? We get new goals. And we get goals for each of our trajectories. So what we end up with is we have trajectory 1 and goal 1. And then we have trajectory 2, and then we have goal 2. This maybe isn't the best way to write this. And we have, as it goes, all these things. And now once we have these, well, we've actually built a data set, right? This is our new data set. of examples. So once we have our data set, we can just go back to our old method. And the method I told you about before, using all the data augmentation and the ARL and all that, they call it LangGoal, I believe. LangGoal IRL. I'm pretty sure that's what they call it. So we use this data set to do a new, essentially, LangGoal IRL training process. And that's kind of the whole thing. It's actually not too complicated. It's fairly nice. And the idea is that from there, we would branch out into all sorts of new actions and learn new goals. And even though we might not have a specific goal in this new environment, we should be able to learn how to do all sorts of things so that when we, the human, go and we want it to do something specific and we give it a language-based goal, like go up the stairs and open the door to the right, well, hopefully it has learned so many things already that it will be able to generalize to this new task. Whew, that was a lot. This is a really complex paper. I had to go over it a few times. There are the results down here. They're fairly good, though I'll go over some criticisms in a second. Let's actually do that now. Let's go over the pros and cons of this paper. So my overall thoughts. Let's start with the pros. Now the pros here are, 1, sample efficiency. Now this was kind of the whole goal of the paper, or at least part of the first half of the goal, right, was to be sample efficient, and that it absolutely does. It's more sample efficient than previous methods, which is great. And the second big pro here is the other thing they were setting out to do, which is the self-supervised learning portion. And now this is my favorite part of this. I love this so much. Self-supervised learning, I think, is really the way towards more general algorithms. We can't spoon feed data to these algorithms for every single little thing they need to do if we want to make agents that can work well in general situations, right, and learn to generalize. So the self-supervised learning portion of this is, I think, a great start of how we can really start making general agents. So kudos on that. I think they did a great job there on this paper. Let's talk about some of the cons, though, because there are some cons here. There are some things to be improved. Now, I think the first one is this is complicated. This paper is just very complicated, not math-wise, but let's scroll back up and look at this algorithm again. Look at this. It's just long. It's not particularly hard to implement, I don't think. I mean, I haven't, but just looking at it doesn't look too hard, but it's really complicated. It would be nicer if it was a bit simpler, but oh well, I guess. This is a minor complaint, but it is there. And the second thing, though, is that this method relies on the VGG completely. So this variational goal generator, if it doesn't work, this entire thing doesn't work. Not at all. We'd probably get worse results than, I don't know, even random maybe, because we're essentially we would be associating the wrong goals with the things we were doing. So if the VGG doesn't work, none of this works. And that another thing here, right, is we don't have a good way to know whether or not this training process is working because it is self-supervised. We don't have any good metrics to measure. Maybe that's something it would have been nice if they added in this paper, but we don't know if it's really working. So we kind of have to trust it or manually check throughout the training process, I would imagine, which isn't very nice. So this is, I think, probably the biggest downside of this is that if the VGG doesn't work, this whole method is bust. And I should mention, and I guess this is the next con, is they only show, or the results are only reported for one type of environment. Now, you might be like, what? Didn't you say they do self-supervised learning and that helps them transfer to a different environment? Shouldn't they have tested that? Well, they did, but they only use one type of environment, and that's this 3D navigational environment. And I'm sure they had some time constraints, but I am very dubious. I have dubious expectations for whether or not this would transfer well into other types of environments, like certain games or robotics or stuff like that. And because of that, it's really hard to tell how well this method actually works and whether or not the VGG would extend well to other types of environments. So that's another bit of a downside. And the last downside here is this method requires multiple policies. Now, specifically, they require a policy for every single different environment you want, which is a lot. That's a lot. It does sort of depend on how you break up your environments. Like you could have one super environment, and then I guess this isn't too bad anymore. But yeah, it's just a little bit of a concern. I think this is something that could be patched up in future papers. So this is somewhat of a minor thing. These two things, the reliance on VGG and the results for only one env, I think are the two biggest complaints here. But that's sort of my thoughts on the pros and cons of this. Overall, I think this is a great paper. I think it's really creative, and it brings some new stuff to the table, or a new way of doing this at least, even though it's using like, all familiar parts. The idea is very novel, and I appreciate that, because lots of papers these days are not, it's just nice to see something novel every once in a while. But anyway, that's all I have for this paper. And I guess we can close it out now. Last thing I'll mention is, again, if you want to catch up with the Zero to Paper series and you haven't yet, you can certainly expect to see more from it. Do consider subscribing. It helps out the channel a lot, and I put a lot into these videos, so it means a lot. Anyway, that is it for this time. Thank you so much for watching, and I hope to catch you next time.